Hello, my friends of Hatari Labs. My name is Saul Montoya. Please welcome to this tutorial, this webinar. In this webinar, what we are going to do is we are going to model a pumping test over a confined aquifer. The history of this webinar is that actually I wanted to implement the TIES solution for a real pumping aquifer. And it was really frustrating because actually Thais, TM, and Cooper Jacob are really idealized conditions of nature. Okay, and in those conditions of nature, actually there are a lot of things going on, um, and not all, and almost in no place can fit to this ideal condition. So that is why I did this, I construct this model that is actually uncalibrated. Okay, in the next part, we are going to do the calibration with neural networks. Okay, and we might do it with PEST. Okay, so uh, you have, this is the link of the data, and this is the link of the data. I'm going to open this here. Okay, and in order to download it, you have to type Hatari Labs with capital H. Okay, and then we download that. If you are here, if you have downloaded the data, if you have downloaded the data, okay. So is how much time? It's quite heavy. I didn't realize that. Mm, 600 megabytes. Yeah. Okay. So if you have when you have downloaded the data, okay, so you are going to copy this and then you are going to paste it under your documents and then you are going to extract here. Okay, great. So if you have this, so this is a backup. So, okay, so if you have this folder under your documents, please type 2. Okay, so we are going to open Anaconda prompt and then see CD documents, CD pumping, I guess, webinar or pumping test analysis with Python with FloPy v1. Okay, and then here we launch Jupyter Lab. Great, that is amazing. Okay, okay, great. So we go to scripts, okay, and then we in scripts we are going to do two parts because the first one is actually the head the construction of the MODFLOW model, and the second part is the comparison between observed and calibrated heads. Okay, so this will be part one. Great. So this is part one. Okay, and then now we are going to type it. Okay, so first we are going to import OS, sys, and copy. These are our core package of Python. Import Matplotlib as NPL. I don't know exactly why I imported that. Import Matplotlib dot py plot as plt, import numpy as np, import pandas as pd, import flowpy. Okay, great. So here shift enter and then we have imported the required package. Okay. So here we are going to define some meta information of the model. So I say sim name. So we have in MODFLOW-6 we have the simulation and the model. So the sim name will be pumping test. Pumping test. So this will actually pumping test. Yeah, pumping test. The length units will be meters. The time units will be days. And where we are going to store the working directory is equal to model. Okay, great. Okay, fine. So, okay. So here on the folder, we have an image of the setup. Okay, you have the entire report as well, but this is the image of the setup. Okay, so what do you have here is this is the pumping well. This is the pumping well. There are 4 layers of 1, 2, 3, and 4. There is a well, the number 30, that is located in the second, okay, that is located in the second layer, while the other, this is the pumping test, so the other piezometer is located here in the fourth layer, okay? And actually it's not that clear which from which which is the well screen, okay, or maybe I didn't pay that much attention, okay, so I just place it in the middle, okay. What else? These are really close in between each other, so let me, because I have translated this to meters, okay, because the the elevation, the surface elevation is 49.007, okay, and this is the depth of the first layer, the bottom of the first layer, the bottom of the second layer, the bottom of the third layer, and the bottom of the fourth layer, and these are the distance from the pumping well. Okay, if you are here with me, please type 4, no 3. If you are here with me, please type 3. Great. So now what we are going to, and this is what I wanted in this webinar, we want to translate this into a FlowPy code, okay? Because how we do translate this, and it was not that straightforward. Actually, it required me some time to do that, okay? So let's see. Let's see. The top is a 49.07. The bottom dict is equal to, so they say, okay, in FlowPy you define a layer, but in this case I have done an abstraction. And what is an abstraction? I have done a process that can, where like in model muse you have the model group like the layer group, and then this layer group can be divided in several layers. Okay, here we can define this. Okay, we are going to define the layer group, and we are going to leave a method that, for example, you want that the layer 3 will be divided in 7 layers. Okay, that will be possible. Okay, so that how we are going to do that, we are going to define a bottom dictionary, okay, that will store the the top elevation, the bottom elevation, and the number of layers that are going to be generated from this layer group, the layer group. Okay, so let's see. And why I have done that? Because on the I did a because I wanted to represent the dynamics of the pumping test, and with few layers it was not possible to represent the dynamic. Okay, because actually with few layers all the drawdowns will be horizontal, so and the impact of the vertical K on the same aquifer will be decreased. Okay, if you have any questions, let me know. Bottom elevation is 32.31, and the layer number will be 2. Okay, this is for layer 1, layer 2, layer 3, and layer 4. Layer 2, 3, and 4. Yes, and this is for 31, 31 to minus 26.29 to minus 57.60 minus 57.62 minus 154.29. And for example, the first layer we are going to split in 2, and the third layer we are going to split in 3. Okay, so we are going to from the second layer we are going to split in 3, so we are going to have 11 layers in the end. Okay, so we are going to do bottom list is equal to repeat list is equal to for key value in bottom dict items. Okay, bottom list dot append mp link space of value of top left, value of bottom left. Okay, and of value link. Link plus 1. Okay, this is an arrangement that generate the layers. Okay, you with and then we use repeat list dot append of value link. Okay, so and the bot m is equal to mph stack, horizontal stack of bot m list, and then we can print bot m, and then we can print the repeat list. Okay, so let's see. Okay, so this will be the array. Okay, based on the because there is a question here from Galmuti and say difficult in the case where same layer don't go across. No, no, actually no. What is the same layer? No, this is a kind of generic. I mean, this is just this I mean, this code is in order to represent the well site that we have done, but if you have another setup, you can also implement it here. Okay. However, in here we represent horizontal layers. These are not so we don't have any special contacts or like slopes. Okay, so these are the bottoms of every layer. Okay, great. But in these layers we have already refined it. So instead of having the four layer as or for the four layer group as a whole, okay, so you are going to find three layers that represent the four layer group. Okay, great. So let's see and let's continue. Yes, nlay is equal to, okay, the number of layers is equal to bottom dot shape 0. That will be actually the sum of the repeat list. Okay, so the encall, here we use 121. The n rows is 121, and the del r is equal to del c, that is equal to, okay, so in the beginning, okay, we have a refinement that is of 4 meters. Okay, in the beginning we have a refinement of 4 meters, and this refinement will be then we shift to 2 meters, and then we shift to 0.5 meters. Okay, so how we do that? We do it with some, we are going to join many lists together. Okay, for e in range of 20. So this will be the outer refinement, plus this will be 2, plus this will be 0.5. Okay, and in this case it's 41 cells, so you are going to see that on the plot. Plus, and I'm going to break this into lines. You are not required to do that. Okay, so you can just put this in the same line. Okay, so oops, what happened here? This is shape 0. Okay, okay, so this is your, well, this is the delar. Okay, so, and then we define the starting heads. Okay, the problem of this setup is that the starting heads per every layer are different, or this is what I have seen according to the data. So what I have done here is that I have given a different starting head per, well, I have given a different starting head per layer. So aph stack of np.array 43.43. Okay, np.linspace of 43.43, 36.033, 3. Okay, great. strt is equal to np repeat, and then we repeat those values. Okay, then we repeat those values. Okay, np repeat of strt 2,3,3,3 repeat. And then we have, this is the array of the starting heads. Okay, great. If you are here with me, please type 4. If you are here with me, please type 4. Yeah, there is a question of Miguel Ángel Bolario that says, uh, each number of the list, okay, if number of the repeat list, okay, is actually, yeah, the values that are going to be, because um, instead of having 4 layers, you have 11, okay, you have, for example, the starting head, you have to repeat it, okay, so that is why we create this repeat list, okay, that is actually the number of divisions of each layer groups. Okay, Miguel Angel, is that clear? Great, great, thank you for your questions. Okay, so I think that this is one of the most complicated webinars that I have given in FloPy, okay, but okay, so we as well repeat of MP array of, because we are going to define the cell type that it will be 1000, okay, and then repeat list. Okay, so we are going to repeat that to the amount of layers that we have. Okay, because this is for, like, say, one, because it's the first layer group will be convertible while the other will be confined. And K11 is equal to MP repeat of MP array of 110 to the minus 3. And these are the difference, the values. And this, and in this case, the K of 3 is equal to MP array of K of 1 divided by 10. SS is equal to 1.0 e to the minus 4. Sy is equal to 0.02. Okay, great. Great. So you have, okay, the values of SS and Sy are not being, do not vary with layers, so it's actually a constant value. So if you are here with me, please type 4, 5. The number of stress period is 7. Okay, because we are going to simulate a steady state plus 3 pumping days and 3 days of recovery. So say per length is equal to 1.0 plus 86, and this is the length of in seconds for E in range of 6. Okay, great. So the number of stress period is equal to 1. And here the number of stress periods, no, this is the number of time steps that can vary to your needs, okay? Why? Because you know that on a pumping test, there is a huge decrease, and then with time, this decrease will be, will diminish. So actually, we are, for example, in this case, we have 8 stress periods for the first day, while in the other we only have 3, and the other for the recovery we have 8, 3, and 3. Mhm. Okay, ts mult is equal to 1.0221211. Okay, this is the multiplier, and we use this multiplier, well, we use a multiplier for the pumping test because we want that our time steps will be much smaller at the beginning and much bigger at the end. TDDS is equal to, and this is the list of zip of per length NSTP tsmult. Okay, and we can show our temporal discretization. Okay, that's it. If you are here with me, please type 6. So we have some parameters for the inner and the outer iteration. The closure, each close. If you have any questions, let me know. Okay. Just in case okay, so we have to sim vs. This is the path of the simulation, os path join vs sim name. So the simulation, where the simulation will be recorded, is here in the pumping test. Okay, so if you change the number of the simulation, so actually it will create another folder. Okay, so exciting. Is there a solver option to continue without converse in FloPy? Yes, there are. I think that is you have to look for the FloPy.mf6 modflow ems. Okay, so I think that there is a relaxation. Oh, yeah, somewhere there is the option of continuing despite no, but you have to look for that option. So okay, so let's create sim is equal to flowpy.mf6.mf simulation. Okay, and here is sim name is equal to sim name. Sim w's is equal to sim w's. And exe name, and this is the executable. This is located in the bin folder, and this is mf6. This is the executable that is also stored here in the, okay, is looking for values here. Okay, great. So we define as well the flowpy mf6 dot modflow tdis, the temporal discretization sim ampere is equal to ampere period data is equal to the this.ds. Okay, time units is equal to time units. Okay, and then we can define the solver as well, flowpy.mf6.modflow ems of sim, comma, outer maximum maximum outer diff close edge close inner maximum and inner dv close edge close close record f close strict. Okay. I have a problem here. Sorry. Here is M. Okay, great. So this is the we have created the simulation, the temporal distribution, and the solver. If you are here with me, please type 7. Any question? I'm going to mark as row just to show you the most amount of code. Okay, great. So we have the GWF is equal to FloPy dot mf6 dot modflow groundwater flow of sim of model name is equal to sim name and say flows is equal to true. And then say flowpy dot mf6. We are going to create the spatial discretization. So it's modflow GWF. This is equal to GWF length units is equal to length units inlay is equal to inlay and row is equal to enrow encall is equal to encall del r is equal to del r del c is equal to del c top is equal to top and bottom is equal to bottom. Okay, great. There is a question from Anjo that says, if we build a grid model in the GUI, is there a way of calling the discretization instead of building the script? Yes, it is possible. Maybe when we are going to do it, yeah, it's possible to do that. I wanted to do it just in FloPy, but it's also possible to do it in, in normal MODFLOW, in Model Muse. Okay, FloPy. Because, Anjo, do you get bored of typing? FloPy mf6 dot modflow gwf mpf of gwf cv options is equal and cv options perch. I don't know why this is perch. Perch true. Interesting. No, we are not going to use the purging option because actually this is not purged. Everything is saturated, so it's eCell type is equal to eCell type. Okay, K is equal to K11. K33 is equal to K33. And save specific discharge is equal to true. Okay. FloPy.mf6.modflow EWF IC of EWF strt is equal to strt flowpy.mf6.modflow EWF storage is equal to GWF eConvert is equal to 1 SS is equal to SS SY is equal to SY steady state is equal to, so because there are three stress periods, okay, and the first one is on the steady state, okay, on the transient, okay, from the second one everything is transient. Okay, great. Okay, I have an error. Length units. Length units. Okay, I run everything again. Length units. Oh, sorry. Okay, I run everything again. So another error. Modflow. Okay, great. So this is the code that does this is the first part of the code. If you have finished that, please type 8. If you have finished that, please type 8. Okay, and this is the, anybody requires more time, let me know. Okay, and then this is the last part of the code. If you are here with me, please type 9. If you are here with me with the last part of the code, please type 9. Okay, now we are going to plot the grid. Now we are going to plot the grid. So I say fig is equal to plt.figure, okay, of fig size of 1010. Okay, ax is equal to fig and then we plot. Okay, so this is your discretization. Okay, if you are here with me, please type 1. And now what we are going to do is we are going to do a cross section. Cross section is equal to FloPy dot plot cross section of model is equal to GWF, and line is equal to row 10. CS dot plot grid AX is equal to AX. And this is a visualization of the cross section. Okay, we have, this is the first layer group. Okay, first, if you are here with me, please type 2. If you are here with me, please type 2. Okay, great. Now we are going to work with the general head, okay, because we have a general head for the surroundings of our model, and then we are going to put the general head. Okay, first the general head. So it's GHB SPD is equal to open and close, because we want a general head that is on the first and the last column and the first and the last row. Okay, and for every layer, okay, it will have a different starting head because there are different starting heads for every layer. Okay, for call in range in call. Okay, GHB SPD plus equal lay call 0 strt of lay, and then the conductance will be 0.001. And this is for the first, this is the first column, then we do that for the last column. Okay, then we do that for the first row and the last row. The first row will be this, and the last row will be in call -1 call. So this will be for the first stress period. And then the GHB is equal to FloPy dot mf6 dot MODFLOW GWF GHB. of GWF, and then stress period data is equal to GHB SPD. Okay, so this is MODFLOW. Great. If you are here with me, please type 3. Then we define the pumping well. It's equal to, okay, so because we have the pumping well for the first stress period, okay, this will be on the layer 9, the column 69, 72, row 72, and it won't be pumping, okay. And for the first it will be minus 0.03648, and this is equal to 579 gallons per minute. And then flowpy.mf6.modflow gwf well of gwf and stress period data is equal to well SPD. Okay, so we have created the well package. Okay, if you are here with me, please type 4. While I did, why I have repeated the well SPD definition? No, no. Here the well SPD is a dictionary where we define different key for dictionary. Okay. And here this is actually 4. This is 4. Okay, because the first stress period, the number 1, 2, okay, the first one is the steady. 1, 2, and 3 are the pumping, and 4, 5, and 6 are the recovering. Okay, great. So, okay, so we define row here. So head file record is equal to f sim name dot hds. And this is the budget file record is equal cbc. Then flowpy.mf6. MODFLOW GWF OC GWF. In what the pumping is in layer 9, yeah, because the 4th layer correspond to index 8, 9, and 10. Okay. Head file record is equal to head file record budget file record save record. This is budget. Okay, so this is the output control package. Okay, and then if you are here with me, please type 5. Okay, so we can write the simulation sim.write simulation. Okay, so it has written the simulation. Where it has written the simulation? Here in model, here on pumping test. Okay, this is the, okay, I'm going to delete what is on my pumping test because it has a previous run. Okay, I'm going to delete everything. So then, okay, then you write the simulation again. And then this is the simulation file. Okay, great. Okay, then we can check. There is a check on FloPy that do some checkings. Okay, and it says that no errors were encountered. Okay, and then we can sim.run simulation, and then we run our simulation. And, uh, ooh, 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 okay, I'm going to rerun again because things can be stored on memory. Oops, sorry. But if I have in memory, everything has to be code. Code, code. Okay, again. Mhm. Okay, yeah, it was a is sometimes it happens that is related to the it's related to the memories. Okay, so it's running. So if it's running for you, please type 6. Okay, so yep, it has finished for me. If it has finished for you, please type 7. If it has finished for you, please type 7. Okay, if it has finished running for you, please type 7. Okay, I will take advantage to show you the coming diploma that we have in FloPy, and this is a diploma that will be given for um, from March to July. It has a comprehensive from the ground on Python to apply the exercise. I mean, it's the opportunity to have sound foundations in FlowPy. Okay, I strongly recommend to take this live. I mean, in this because actually it will be recorded and also available on this platform. Why I recommend to take live? Because you can make questions and then you can go with the pace of the diploma, and then you can instead of learning by your own, you are going to learn accompanied, okay? And you can, and then you are going to have live support as well. Okay, so this is the link, and we don't know. I mean, we actually don't know when we are going to give this diploma again. So, so, so if you are hesitant of taking this time, so we don't know when it's going to be next time. So I strongly recommend that you, and then if you pay before the 31 of December, you are going to have a discount. Okay, and for the Spanish speaking attendees, so we have as well the same link. Okay, so this is the link. Okay, great. I hope that you can join us here. Okay, we have typed a lot, okay? And what we are going to do in the scripts, we are going to open this head comparison. We are going to open that because it's actually more typing, okay? And we are going to kernel, restart and clear all outputs. And then we are going to run the first, okay, we open the observed head, and this will be the the simulated heads. And there is a problem here that says there is not such thing as model pumping test, and this is pumping pump. Okay, pump test. Yeah, that is right. Yeah, that is right. There is no why, because here we are missing a cell. Okay, here we are missing a cell. Okay, so we have after the output control, there is a cell that is missing, and the cell that is missing is the observation point. Okay, so ops dict is equal to open and close uh, ops list is equal to, okay, and this case is this name J025. This is the observation point. Okay, and this will be 96150. Okay, Okay, this is the 29 and this is the 30. And these are the observation points. Okay. Okay, 961.50, 961.72, 361.61. Okay, great. So say ops dict is equal of f sim name dot ops dot head dot csv. Okay, is equal to ops list. Ops is equal to FloPy dot mf6 dot MODFLOW ult MODFLOW utl ops gwf print input false continuous continuous is equal to obstict. Okay, and then we run everything again. Okay, because okay, we have run the model, but actually defined we haven't defined the output, so that is why the model. Okay, so ops list ops ops list. Actually, this is in lower. Ops list ops dict. Okay, just make it uppercase. Okay, ops dict ops list. Okay, and this is ops list. Print input. Okay, write the simulation, sim check, and run the simulation. Okay. If when it has finished running, okay. So we have to rerun everything again. Okay, bye, Paul. Okay, this is obstict. Okay. So when it has finished for you, please type 7. So when it has finished for you, please type 7. Okay, it's running. When it has finished running for you, please type 7. This is the code of the missing code. When it has finished running for you, please type 7. Mhm. Okay. Did the US, okay, there is a question from Mike that says, did the USGS report provide the initial key values? No, yep. You have the report here, and the report here that is here on images. You can read the report and then no, but I actually haven't used those values because I was playing around. Um, okay, but the reported values are there. Okay, Mike. Okay, so it has finished, and then we can run our code. Okay, so these are the simulated values, and this is from the observation package. And then we have the observed data, and then we can plot the comparison. Okay, this is a comparison. This is for the J25, and then as well we have for the J29, that is the pumping well. And on the pumping well, we have only the recovery. Okay, we only have the recovery. And then here we have for the 30, and the 30 is on the second layer. Okay, and there is some, okay, because actually there was not that much impact on the second layer due to the pumping. Okay, so that will be the for today.